if you've made it this far, you're probably getting a little frustrated. I've had existence and uniqueness up on the board. We teased it first thing, and then we did all these tangents. We talked about homogeneous and operators, and we talked about linear independence and Wronskians and blah, 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 blah. When's the good stuff coming? Well, finally, it's time to talk about it. So it turns out that every nth order homogeneous ODE, remember those are guys with the form LU equals 0, has n linearly independent solutions, which we call its fundamental solutions. And then, moreover, when I build a linear combination of those guys that builds an n parameter family of solutions, we know from the principle of superposition that this guy also solves the ODE. And we call this solution that contains every piece of fundamental information, the general solution to the ODE. So just to get used to that vocab for a second before I dive into justifying this really bold claim, I want to remind you of that very first example we looked at. We saw the differential equation omega double prime plus 16 omega equals 0. You'll notice that this is a second order linear homogeneous differential equation. So it satisfies the criteria. And what I can immediately learn from this is that I have two fundamental solutions. But when I posed the problem to you earlier, I just gave you, and in fact I may have even called it the general solution without explaining what that term meant, but I know that anything of this form is a solution without specifying any initial or boundary conditions, right? This is a solution, and it's a two-parameter family of solutions. And you may have noticed this pattern by now, that I have two parameters for an order 2 equation. Here's why. Now, again, this is the general solution. That's the general solution of my equation. And I should be able to extract the fundamental solution from this equation. Here we can almost do it visually or by inspection. I see I've got a linear combination of these two things. So it's tempting to say, hey, look, there's my fundamental solutions, but we should verify first that those guys are linearly independent. How do I do that? The Wronskian, of course. So let's do it. Here, at least, I only have two functions to look at. I've got cosine of 4t and sine of 4t. And remember, I start building a matrix. I put all my functions across the top. And I keep taking derivatives down until it's square. Here I just need one more row to make it a square. So I'll get negative 4 sine of 4t. And I'll get positive 4 cosine of 4t. Taking the determinant, multiplying down, I get 4 cosine squared of 4t. Multiplying up, I get negative 4 sine squared of 4t, but I'm going to subtract that. So plus 4 sine squared of 4t. Factoring out the 4, I have cosine squared plus sine squared of anything is 1, so 4. And that is surely non-zero. Doesn't matter what interval I'm looking at. So great, these are linearly independent. They are the fundamental solutions. So y1, being cosine of 4t, is a solution, and y2, being sine of 4t, is also a solution. And it would be a good exercise to verify that those are solutions. Okay, so quick reminder of the claim that I made, and here I'm just showing the argument for second order, but it's pretty easy to at least extend the ideas to higher order, though the fine-grained details get a little messier. So, if U1 and U2 are a fundamental set of solutions to this is the linear homogeneous second order equation, written generally. Then there are some constants, C1 and C2, such that this particular linear combination of the fundamental solutions is the general solution. So first of all, it's really easy to get the linear independence tied up in your head, because U1 and U2, if their fundamental solutions are linearly independent, and that means that we cannot add them up to 0 in any meaningful way anyway, just trivially. But this linear combination of them, we know is a non-zero function then, at least non-zero in somewhere on our interval. So this linear combination is non-zero, yet it still satisfies the differential equation. So that's the striking part on the grounds of linear independence. But the other issue, maybe the more glaring one, is that, well, we just talked about principle of superposition earlier. Duh, that's a solution. And you're right, duh, it's a solution. The principle of superposition tells us that. But it's not obvious that it's the general solution. Remember, the general solution to a differential equation is a parameter, or is a family of solutions, in this case a two-parameter family of solutions, from which every other solution can be obtained. So it's not immediately obvious that this is the general solution. Just wanted to clear up those nuances before we get started, because those are some thoughts I had when I was learning this for the first time that made it difficult to see why we should bother with it in the first place, but it's worth bothering with, so let's bother with it. All right, first things first, I am going to extrapolate what does the information from our assumptions tell us. So, the fact that U1 and U2 are fundamental solutions tells us two things. First of all, they're solutions, right? So it tells me that L of U1 is 0 and L of U2 is 0. So what that tells me, we've already briefly mentioned in words, by principle of superposition, I guess PSP, not PlayStation Portable, but principle of superposition, we know that U, capital U, what I've called over here my supposed general solution, is a solution. Great. That's off to a pretty good start. We know it's a solution, but is it the general one? To get generality, we're going to need to use the other key part of our assumption that's a little understated. Because they are fundamental solutions, these two functions are linearly independent from each other, right? So that means two things. Since U1 is linearly independent from U2, I get the following two pieces of information. First of all, I know that I cannot take a linear combination that adds to 0, or at least adds identically to 0, right? So any C1U1 plus C2U2 is non-zero. And that's important because this guy tells us capital U is a non-trivial solution. The other piece of information it tells us is that their Wronskian is also non-zero. And it's a little less obvious why that's going to matter, but let me show it to you. In order to see the importance of this piece, though, I need to rephrase my problem just a little bit. Now, if U, my general solution here, is a well-defined function, we've already said it's not a trivial solution, we've already said that it is a solution on I, then if I pick some t value, I'll call it t naught in I can artificially define some initial conditions, right? I know that big U of t naught should equal some number, because it's a non-trivial solution there. We'll call it u naught for now. And u prime, of t naught is equal to, we'll say u1, some other number. Remember, we're assuming for the moment, or remember, u is not equal to 0, LU is supposedly equal to 0, right? So I'm going to artificially define this initial value problem. And if you take a look here, u, we already know, is C1 U1 plus C2 U2. And we're saying that at T naught, this is equal to U0. U prime of T, however, is just going to be C1 U1 prime of T naught plus C2 U2 prime of T naught equals U1. And now, because I know U1, little u1 prime, little u2, and little u2 prime, right? These are known solutions to my equation. This is really a system of linear equations. And it has the form, if I write it in an augmented matrix here, I've got the things I'm trying to solve for are C1 and C2. So my coefficients are U1 at T naught. Remember, that's just a number. U2 at T naught. U1 prime at T naught. U2 prime at T naught. And this times C1, C2 is equal to U naught, U1. By the way, I understand now I'm kind of dipping into linear algebra territory. So if this part is confusing to you, I would recommend you skip ahead to this timestamp on the screen where I'm done with all the linear algebra arguments, and I will do a quick recap at that point of the important takeaways that you need without knowing the linear algebra. So, if you recall from linear algebra, the system ax equals b is uniquely solvable if A is invertible. And A is invertible if and only if the determinant of A is non-zero. Does that determinant look familiar? The determinant of A is the Wronskian of U1 and U2. So what does all of that say? The Wronskian of U1 and U2 not equal to 0. This tells me that my system of equations has a unique solution. There are unique C1 and C2 such that these guys, right? Such that U of T naught equals U naught and U of prime of T naught, equals U1. All right, time for a quick recap. Because we've made a lot of bullet points of relevant information, I'd like to zoom out now that all of it's here so that we can see the core logical skeleton, I suppose, of this proof. The first thing is, principle of superposition told us this guy is a solution to begin with, right? We know it's a solution because each of these are solutions. So a linear combination of them is also a solution by principle of superposition. Next, we know it's a non-trivial solution. Because U1 and U2 are linearly independent, remember that's part of being in the fundamental set of solutions. Because they're linearly independent, I know a non-trivial linear combination of them is itself non-zero or non-trivial. So not only do I know U is a solution now, but now I also know it's a non-trivial solution, getting warmer. From here, linear independence also gives us that the Wronskian of U1 and U2 is non-zero. And we built up this artificial initial value problem that showed us the constants C1 and C2 can be uniquely determined. In other words, they are guaranteed to be, well, to exist in the first place and to be non-trivial. So now we know that U is a proper two-parameter family of solutions. The last thing that remains is to know if all initial value problems solutions can be derived from this family. But that's exactly what we did to get this to begin with. So we have shown that U is a non-trivial two-parameter family of solutions from which all initial value problems of this form can be, their solutions can be derived from this function. Therefore, by definition, U is the general solution to this ODE. And I'd love to be able to end the video there on that really impactful note, but I just want to be as clear as I can about what things exist and are unique, because I've been throwing those words around a lot. Solutions definitely exist to the homogeneous, linear, nth order differential equations. In fact, we know there's at least n of them. Right? We know there's at least n of them. Those are the fundamental solutions. So we know that many solutions exist to just the equation. It is still true that we require n initial conditions in order to get uniqueness out of those solutions. The general solution that we just worked with together here, this guy, is evidence of that. It's an n-parameter family of solutions. And all solutions to the homogeneous differential equation derive from this form, or they can all be written in that form. Even the fundamental ones. Notice if I take C1 to be 1 and all the other C's to be 0, I get the first fundamental solution. Rinse and repeat on all the other indices there. When I have initial conditions, I get a unique solution though. Moving forward, we're going to have to analyze what aspects of a differential equation give us existence and uniqueness. Moreover, moving forward, I'd like to talk about more than just linear and homogeneous equations. In particular, we could just move to non-homogeneous equations. Stay tuned for that one.